Okay, ELE 115. This video is about the Week 6, Unit 7 practice quiz problems that were, that are about RL series circuits. And so I put together this document which you can find here. Resistive, inductive practice circuit problems solutions. Talk about a giveaway. There's some sort of thing up here with test scores and all that. And as I think I said in my last video, at least one student had indicated that they weren't sure that these tests were capturing the right numbers and giving the score as they should, and may have had some answers that were either close or wrong or something like that. And I took these tests myself, and there's two problems in the test, and I got an 85 out of 100, and I taught the person who made up these tests how to do AC. So I think I'd like to just walk through them and solve them as I would, and see if it helps you to understand that sort of thing. So let's go over here. This is that document that I just pointed out. Resistive inductive practice circuit problems solutions. So we have a 10 volt peak to peak 1 kilohertz source with no DC offset, just pure AC. We have 2,200 ohm 2.2 k ohm, if you will, resistor, and a 100 millihenry inductor. So now I think these were some of the scores I gave, and some of the answers I gave, and apparently there was they didn't agree with them. But rather than trying to pick out answers from a list like this, I'd like to just do the thing, and you can see what the answers ought to be. Okay, let's solve this thing the right way. So just the thing to remember here, 2.2 K, 100 millihenries, and 1 k ohm, and of course 10 volts peak to peak. So we come down here and we note that, I want to make a note here. When I first learned electricity, E was used for voltages. Then, as we went into the 1900s, V became popular. Our book seems to like to use E. So just note that V total and E total are the same thing, just like ER and EL are the same things as VR and VL respectively. So when you see me using V's, that's voltage, and E would be the same thing. So again, we're at 1 kilohertz, okay? So 2 pi FL, you got your 2 pi, you got your F here, 1 times 10 to the third, and you've got 100 times 10 to the negative third, that's L. So that's, this one is hertz, this one is henries. But when you multiply them together, the 10 to the third and the 10 to the minus third cancel out, because you add the exponents when you multiply numbers of the same base. So plus 3 minus 3 comes out to 0, and I get 2 pi times 1 times 100. Well, 2 pi is about 6.28-ish. 100 times that is 628 and change. So that's our that is our inductive reactance. Once again, when we make our impedance chart here, this construction, inductive reactance is on the reactance axis, or the imaginary axis, and inductive reactance points up. If we had capacitive reactance, it would point down. So I have a resistor value of 2200 ohms, and I have an XL inductive reactance of 628.32 ohms, and I build my my two components, and the resultant vector is right, let's do our calculation here. So Z is this Pythagorean theorem, right? It's a right triangle. I got this height and this base. So I'll take 628.32 and square it, add to that 2200 squared, and if I want ZT, I'll have to take the square root of the sum of that, and I'll get 2288 ohms. Kind of interesting. It must be a pretty low angle, because the difference between 2200 and 2288 isn't that big. So now let's look at our phase angle. Our phase angle, remember SOHCAHTOA, tangent equals opposite over adjacent. The opposite is 628.32, adjacent is 2200. So we want the angle whose tangent is 628.32 over 2200, and that angle turns out to be about 15.94 degrees. So I now have the total impedance is 2288 ohms at 15.94 degrees. Just like we did with the lab problem video, we're going to find the total current. It will be the total voltage divided by total impedance. And so I have 10 volts peak to peak at 0 degrees divided by 2.288 k ohms at 15.94 degrees. So I do all this stuff, and I wind up with a current of 4.347 times 10. Now, this guy is, the way I wrote it, this guy up here is 10 times 10 to the 0. 10 to the 0 is 1. This guy is 2.288 times 10 to the third, and 0 minus 3 results in a negative 3. So, let me just deal with that, okay? And go back to our document here. Sorry about that. So we wind up with 4.37 times 10 to the minus 3 amps peak to peak at 0 minus 15.94 degrees. 0 degrees minus. So the total current is 4.37 milliamps, that's 10 to the minus 3, peak to peak, at minus 15.94 degrees. And once again, current lags in an inductive circuit, so we have a negative angle here. Now the voltage across the resistor, now that we have the current through the resistor, voltage across the resistor is IR times R, right from Ohm's law. Well, turns out that in a series circuit we only have one current, and we know that total current is IT, so that's the same current that flows through the resistor. And that's important, like I said before, because that means if we can measure the voltage across the resistor, we know what the phase of the current is going to be, because there's no phase change in a resistor. So we take our 4.37 times 10 to the minus 3 amps peak to peak, that's 4.37 milliamps peak to peak, at minus 15.4 degrees times 2.2 k ohms, that's the 10 to the 3, at 0 degrees, and VR turns out to be 9.615 times 10 to the minus third times 10 to the plus third, which is basically this. There's the minus 3 and the plus 3 there. They're going to cancel out at minus 15.94 degrees plus 0 degrees, and so basically we get 9.615 volts peak to peak at minus 15.94 degrees. Same phase angle as the current. The voltage across the resistor has the same phase angle as the current. That's why taking a look at the voltage on an oscilloscope of a resistor in a series circuit like this gives us the phase angle of the current, because resistors convert energy to heat immediately, and do not delay your signal or distort it. Now, they ask for the true power in milliwatts. Well, true power must be calculated from RMS quantities, okay? If you look at a sine wave, this is a pretty funky looking sine wave because I made it out of graphics objects, but if you look at this sine wave, this has no DC offset. Forget about that. We're just talking about a pure AC sine wave. The voltage from 0 up to the peak is called V peak, all right? And the voltage from the positive peak to the negative peak is called V peak to peak. Those are interesting, and they're both peak to peak voltage is especially useful on an oscilloscope because you can see it. It's very graphic and easy to pick out. VRMS. RMS means square root of the mean square, and what it is it's the power producing equivalent of an AC signal. If you looked at the signal, and I don't recommend doing this unless you really know what you're doing, if you look at the signal coming from the AC line, you would see that the peak voltage is about 169 volts, and that swings down to minus 169 volts, and that gives you a peak to peak of 338 volts, and obviously a peak voltage of about 169 volts. But we call that voltage, people call it 120 volts AC. Turns out that's the RMS equivalent, and obviously the peak is half of the peak to peak, or the peak to peak is twice the peak. The RMS is equal to the peak voltage divided by the square root of 2. So V total RMS is 10 volts peak to peak. Actually, what am I saying here? V total RMS is equivalent to 10 volts peak to peak, is equivalent to 5 volts peak, and the real RMS voltage is 3.5355 volts. Now let's go back to that power line example, for instance. The power out of the wall is rated at 120 volts AC RMS. If I took 10 12-volt car batteries and connected them in series, I'd have 10 times 12, or 120 volts. If I plug that into a resistance heater, it would warm up the room at a certain rate and to a certain level. If I have 120 volts RMS AC and I put it into a resistance heater, it will warm the room up exactly the same as 120 volts DC, because we're talking about direct conversion of electricity to heat. That power and energy calculation has equivalence between AC and DC. So the AC equivalent to heating something up with DC, or the AC equivalent to doing any work with DC, is the RMS value of the AC signal. So our total voltage, that 10 volts peak to peak, is actually 3.5355 volts RMS. And we can go through the same thing. The total current RMS is equivalent to 4.37 milliamps, which is a peak-to-peak value. I got to divide it by 2 to get it down to peak, and then I got to divide it by radical 2 to get it to RMS. And we find out that the RMS current is 1.545 times 10 to the minus 3 amps RMS, or 1.545 MA RMS. All right. So now we have both our voltage, our total voltage, and our total current in this RMS system. Okay, so the total power is equal to our RMS voltage times our RMS current times the phase angle. The cosine of the phase angle, which you may remember, is this thing called power factor. So I do all that, and I wind up with, let's see, a couple things we can calculate here. I wind up with 5.25 milliwatts of real power, okay? Because I put the power factor in there in terms of cosine of 15.94 degrees. PVA is the apparent power, and that's equal to 5.46 millivolt amperes. So, you know, the apparent power is 5.46 milliamps, but the real working power, the power that could do anything, is 5.25 milliwatts. And the power factor is the cosine of the angle times 100%. So it comes out to 96.15%. When you're up, you know, the closer you are to 100%, then you know, the maximum amount of your power is going to real work and doing something. And the power company likes that. Now, the voltage across the inductor equals the IL times X sub L, and that's just an Ohm's law relationship. VL equals IL times XL. It's like V equals IR. So we have our total current 4.37 milliamps peak to peak at minus 15.94 degrees times the inductive reactance of the coil, and that's at 90 degrees because straight up and down, and what we get is 2.75 volts peak to peak at 74.06 degrees. And this inductive reactance with the 90 degrees, that sets the place where the current, you know, you do some calculation here, and you'll note that once again the current and the voltage across the inductor are out of phase by 90 degrees. In practice on your scope you probably won't see that because the inductor can't be perfect. It's got some resistance due to the wire used to wind the coil. But that's how we get VL. And again, when I'm multiplying, you know, if I had exponents, I would add them, you know, exponents of the same base, I would add them. And phase angles, I would add them. So that's how I go from 90 degrees and with minus 15.94, I go to 74 degrees. Does the current in the inductor lag the voltage across the inductor by 90%? Well, let's check. That's one thing. Well, we did check. This 90 degrees in this formula actually forces that to happen. But if you look at 74.06 and 15.94, when you add them together, you get 90. All right. So the difference between the current and voltage in this circuit is 90 degrees. In reality, this would, you know, you wouldn't, this guy wouldn't be quite as high, and the scope would be telling you, you know, this isn't quite 90 degrees. Now the other check we can do is this one. Does the current in the inductor lag the voltage across the inductor by 90 degrees? Yeah, that's the one we just did, I'm sorry. Does this, and this is a voltage rule, does VT have a Pythagorean theorem relationship with VR and, oh, that's a typo, and VL, so sorry. So VR is 9.2 615 squared. VL is 2.75 squared. And is that equal 10? And I think you'll agree that it is. This is quiz problem 2. So now we're at 7 volts peak to peak, 1.5 kilohertz, 220 ohms, and 10 millihenries. There's my answers. You can laugh at them if you like. So we do the same process again. This is just the same problem at a different frequency, different values. XL equals 1.5 times 10 to the 3 hertz. That's 1.5 kilohertz. And 10 times 10 to the minus 3 is 10 millihenries. And I multiply by 2 pi, and I wind up with 94.25 ohms. I look at my impedance chart. I put my inductive reactance vertically on this axis here. I get 94.25 ohms that way at plus 90 degrees. And then for the motor and for the resistor, I have 220 ohms. All right, and so you put those together. Now you've got your classic Pythagorean theorem problem. There's XL, here's R. So now we can do this. The total impedance, at least the magnitude of the total impedance, equals R squared plus XL squared, taken under the square root. I do the calculation. I get 239.34 ohms, and the phase angle, again, it's the angle whose tangent is this opposite over that adjacent. So you just got to plug your numbers into the angle whose tangent formula, tangent, inverse tangent, arc tangent, whatever you call it, and you get 23.19 degrees. Now, so we've got ZT is 239.34 ohms at 23.19 degrees. Great. Once again, we're going to go find the total current with Ohm's law thing. We got total voltage divided by total impedance. We go do this thing, 7 divided by 239.34, and 0 divided by 23. And so we're going to get an answer of 29.25 milliamps at 0, at basically at negative 20.19 degrees. And the current, here we go. Current is lagging again, negative phase angle in an inductive circuit. VR equals IR times R. That's your Ohm's law. No surprises there. We can substitute IT because it's a series circuit, times R, and we take 29.25 milliamps per milliamps peak to peak at an angle of minus 20 times 2.2K at 0 degrees, because resistors always are at 0. So when we multiply that all out, we get 29.25 milliamps times 10 to the minus 3 amps peak to peak times 220 times 10 to the 0. So VR winds up being equal to 6,435 times 10 to the minus 3 volts peak to peak at an angle of minus 15.94, plus 0 degrees because we're multiplying by resistance here. And what we get is 6.435 volts peak to peak at minus 15.94 degrees. Now that's great. So now I got the voltage across R. I've got the total impedance. I know the total current. And now, once again, we have the old spiel about power. True power is in watts and has to come from VMS quantities. RMS quantities, sorry. Our voltage total in RMS is equivalent to 7 volts peak to peak, 3.5 volts peak, and 7.47 volts RMS. So we now have our RMS voltage. We do the same thing with the current. We got to get the RMS current. I've got a peak-to-peak current. I've got to divide it by 2 to get to peak, and then divide it by radical 2, the square root of 2 to get it to RMS. I run through all that stuff, and I get 10.34 milliamps RMS. Now I can multiply those together and keep the keep the phase angle there, because if this were a DC circuit, I'd be done just multiplying the two DC factors together, voltage and current. But with AC, I've got RMS, and I've got to make sure, if it were a resistive circuit, I would just multiply them together and that's it. But if it's not, well, I then have to obey the the power factor constrictions and constraints, if you will. So total power equals 2.47 volts RMS times 10.34 milliamps RMS times the cosine of that angle, which I believe is correct, and I get 23.48 milliwatts. And I really should have put a subscript on there, milliwatts RMS. PVA equals PVA, this is our apparent power, PVA volt amps, equals the total voltage times the total current, and we don't take into account the phase angle. This is just the apparent power. So 3.5355 volts times 10.34 milliamperes, and you get a number here that's 25.54 millivolt amperes. And you can see it's got to be bigger than, it's got to be equal to or bigger than the real raw power in there. So we could say our circuit, if you look at the cosine of 23.19% and multiply it by 100, degrees, and multiply it by 100 to get percent, you're down here, and the power factor is 91.92%. It's based on the cosine of the phase angle, times 100%. People talk about power factor in percent, but when you do calculations, you got to either obey the percent or take it out and use it as a fraction. The voltage across the inductor, we keep applying Ohm's law, but we just keep track of the fact that we're at various phase angles. So the voltage across the inductor is equal to the inductor current, which is the total current, which is 29.25 times 10 to the third amps peak to peak, and we get and that is at the phase angle of minus 23.19 degrees. We're going to multiply that by the inductive reactance. It's IL times XL. So IL, again, 29.25 times 10 to the minus 3 amps peak to peak at minus 23.19 degrees, times XL, whose magnitude is 95.24 ohms at plus 90 degrees, gives you approximately 2.76 volts peak to peak at 66.81 degrees. And we say, does the current in the inductor lag the voltage across the inductor by 90 degrees? It does. And it's simple because that factor, of 90 degrees changes the multiplication, adds in 90 degrees. So of course, and does our Pythagorean voltage test hold? Yeah, 6.435 squared plus 2.76 squared is equal to 10. So there's, two examples going through and just calculating this stuff for RL series circuits, and I hope this helps somewhat. Like I said, I'll produce another one that looks at capacitive circuits before we do the lab on Friday. Alrighty. Take it easy, and thanks for listening, and I hope this helps. Bye.